In this lecture, we're going to start Chapter 2, Functions and Graphs. Section 2.1 covers basics of functions and their graphs. So let's start with the definition of a relation. Just think of a relation as any set of ordered pairs. It doesn't matter what the graph looks like. As long as you have a set of ordered pairs, that's considered a relation. The set of all the first components of the ordered pairs is called the domain, and the set of all the second components is called the range. So think of the domain as the set of all the possible x values in the relation, and the range is the set of all the second components, which would be all your y values. So let's look at example 1, finding the domain and range of a relation. So we have the ordered pairs 0, 187, 1, 212, 2, 225, and 3, 238. So the domain in this case would be the set of all the first components, the 0, the 1, the 2, and the 3. And we could list them in a set. So notice I'm writing the set notation brackets, right? I'm not using my interval notation, which would be either the square brackets or the parentheses. So these guys are your set brackets. And the range is going to be the set of all the second components. So the 187, the 212, 225, and 238. So we'll list them: 187, 212, 225, and 238. So that would be our domain and range of that relation or that set of ordered pairs. Next, let's talk about the definition of a function. You've probably heard of a function before, right? In one of your other math classes. A function is just a correspondence from a first set called the domain to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. So what does that mean? We'll look at example 2. We want to determine whether the relation that's given is a function and give the domain and range. So the key to a function is that for every element in the domain, it's paired with exactly one element in the range. So if we have an element in the domain that's paired with more than one element in the range, it's not a function because it breaks that rule. So look at example 2a. So I have the ordered pairs 1, 2, 3, 4, 6, 5, and 8, 5. So my elements of my domain are 1, 3, 6, and 8. Each one of them only points to one different y value. 1 points to 2, 3 points to 4, 6 points to 5, and 8 points to 5. It's okay if a different element of the domain, if two different elements in the domain point to the same y value. You just can't have an element in the domain that's paired with two different y values. So it can't be pointing to two different y values or elements in the range. So in this case here, and you know what, I'll do it for this first one. Sometimes it's nice to make an hour diagram. So look, for my x values, I have 1, 3, 6, and 8. For my y values, I have 2, 4, and 5. So 1 points to 2, 3 points to or is paired with 4, 6 is paired with 5, and 8 is paired with 5. But notice each element of the domain corresponds to exactly one element in the range. So the relation in example A is a function. And we want to list the domain and the range. So the domain in this case, which I'll just call D, is 1, 3, 6, and 8. And then the range, which I'll call R, is 2, 4, and 5. We don't have to list 5 twice. 5 is 5. Now look at B. We have 2, 7, 6, -1, 1, 5, and 2, 4. Notice now I have 2, which is paired with 7, but 2 also corresponds to 4. So you see how this element in the domain is pointing or corresponds to 2 different elements in the range, and that breaks the rule of being a function. And we'll do an arrow diagram again, because I think sometimes it's easy to see it with the arrow. So look, for x, we have 2, 6, 1, and 2 again, right? And then for y, I have 7, -1, 5, and 4. So 2 points to 7, 6 points to -1, 1 points to 5, and then 2 also points to 4. So you see how 2 has 2 arrows coming out of it. So it's pointing to 2 different y values. So this relation does not represent a function. And the trick is when you're looking at a set of ordered pairs, if there's an x value that repeats itself more than once, it's not a function because then it's going to be pointing to more than one y value or element in the range. So the domain in this case is 2, 6, and 1. And then the range is the set of all the y values. So 7, -1, 5, and 4. We can also determine if an equation constitutes a function. So another way that a function or a relation can be written, so a relation could be written as ordered pairs, but it could also be written as an equation. If an equation is solved for y and more than one value of y can be obtained for a given x, then the equation does not define y as a function of x. So look at example 3. We want to determine whether the equation defines y as a function of x. So in other words, think of x and y as having a relationship. In A, the relationship is that x plus y equals 5. So if I input a value for x and then add y, I should always get 5. So then would this constitute a function? Meaning for every one value of x that I input into this equation, is there only going to be one value of y that we would need to add to x to get 5? So for every x, it should only correspond to one y. So an easy way to do this is solve for y. So let's solve for y. So let's subtract x from both sides. So we're going to get y equals 5 minus x. So now imagine plugging in any value for x. Are we always going to get just one y value? So if I take 5 and subtract x, I'm only going to get one answer, right? I would never get more than 2 values for y. So like if x was 0, 5 minus 0 is 5. It's not going to be 5 and 7, right? That doesn't make any sense. It's just one answer. If x was 1, 5 minus 1 is 4. It's just going to give me one value of y. So since there's only going to be one value of y that can be obtained for a given x, then we could constitute this relation as a function. So we can say that y is a function of x in this example in A. So now let's look at B. Let's do the same thing. Let's solve for y. So if I add x squared to both sides, I'm going to get y is equal to, I'm just going to, well, it doesn't really matter, 16 plus x squared, right? So think about it again. If I input a value of x into this equation, am I only going to get one value of y? So for example, if x was 0, I would have 16 plus 0 squared, which is 16, just one value of y. If x was 10, 10 squared is 100. 16 plus 100 is 116. That's just one value of y. So no matter what value I plug in for x, I'm going to square it and add it to 16, but it's only going to give me one value of y. So again, y would be a function of x in this case, because for every x, it only corresponds to 1y. But look at example C. Let's solve for y again. So I'm going to subtract x squared from both sides. So I'm going to get y squared is equal to 1 minus x squared. Now, I don't want y squared, I want y, right? So I have to take the square root of y squared. So then I'm going to have to take the square root of 1 minus x squared, right? So I'm going to get y is equal to plus or minus the square root of 1 minus x squared. Remember, when we use our square root property, I have two roots, a positive and a negative. So y is equal to positive or negative square root of 1 minus x squared. So now look at this case. If I plug in a value for x, let's say 0, I'm going to get 1 minus 0, which is 1. Square root of 1 is 1. But I have positive and negative 1 as my output. So now I'm getting two outputs for y. So even though I'm plugging in one value for x, let's say 0, I'm getting two values for y. So that one value of x is corresponding to two values of y. And remember, that does not define y as a function of x. So in this case, since y, is going to one value of x when I plug in is going to give me two different possible values for y, we say this relation is not a function. So y is not a function of x. So now let's talk about function notation. You probably remember this, f of x, right? What I just circled here is not f times x. We read it as f of x or f at x. This just represents the value of the function at the number x. That's how we interpret that. So for example, look at number 4, example 4. It says, evaluate the function at the given value of the independent variable and simplify. So let's just review independent versus dependent variables. And let me go to the whiteboard for a minute. So remember, typically the independent variable or the input, think of independent as the input, is x. And then the dependent variable or the output is y. So if we look at this example, if my function f of x equals x squared minus 2x plus 7, and I want to evaluate f of negative 5, what that means is evaluate the value of the function, or in other words, tell me what y is if the independent variable or the input is negative 5. So I also want you to write down y is equal to f of x. So in this case, f of negative 5, so I'm going to input this into my function, is going to be equal to, instead of x squared, I'm going to replace x with negative 5 squared minus 2 times x, but for x, I'm inputting negative 5, and then plus 7. And now we can evaluate that. So let's evaluate negative 5 squared minus 2 times negative 5 plus 7. So negative 5 squared is 25. Now I have a minus 2 times a negative 5, and that double negative is going to become positive. So that's plus 10 and then plus 7. And that's going to be 42. So f of negative 5 is equal to 42. So when I input negative 5 into my function, the output is 42. You could think of this as an ordered pair too. So if I were to graph this function, x squared minus 2x plus 7, the point -5, 42 would be on that graph. Think of it that way. So let's look at the next example. Part B, my function f of x is equal to 4x plus 5, and I want to evaluate f of x plus 3. So we don't always have to input a constant into our function. We could input a binomial, a polynomial expression, like in this case, x plus 3. But it's the same. Think of it as the input. So f of x plus 3 is going to be 4 times x, but we're replacing it with x plus 3 and then plus 5. And now we could simplify that, right? So we're going to get 4x plus 12, right? Distribute the 4 and then plus 5. So we're going to get f of x plus 3 is equal to 4x plus 17. So again, we're not always going to get a real number, not a real number, but a constant when we evaluate a function, right? Like in this case, we evaluated the function at a polynomial, binomial, right, in terms of x. So my answer is going to contain x also. So let's look at part C. So in C now, we want f of x plus 2. So let's evaluate the function at x plus 2. So for x squared, I'm going to have x plus 2 squared minus 10 times x plus 2 and then plus 3. Now this one requires a little bit of algebra, right? Because x plus 2 squared is really x plus 2 times x plus 2. And then we have minus 10 times x plus 2 plus 3. So we have to do FOIL, right? Our distributive property on the x plus 2 times x plus 2. So we're going to end up with x squared plus 2x plus another 2x plus 4. Now distribute the negative 10. So I'm going to have minus 10x minus 20 plus 3. And now we can combine like terms. So I'm going to have x squared. Now I have the 2x and the 2x is 4x, and then we have a minus 10x. So that's going to be a minus 6x. And then I have a 4, a negative 20, and a 3. So that's going to be minus 13. So f of x plus 2 is equal to x squared minus 6x minus 13. Let's do one more. We'll do D. So D says h of x, and we don't always have to call the function f. Like in this case, it's called h. So h of x is equal to x squared plus 2x minus 4. And we want to evaluate h of 3a. So what's the value of the function if we input 3a in for x, right? So wherever we see an x, we're going to replace it with 3a. So we want to find h of 3a. So we're going to have x squared, so 3a squared plus 2 times x, but that's 3a, and then minus 4. So 3a squared is 3a times 3a, which is 9a squared. 2 times 3a is plus 6a, and then minus 4. So h of 3a is equal to 9a squared plus 6a minus 4. So that's how we evaluate a function at a given value, at a given input. So next we're going to look at graphs of functions. And a graph of a function is just a graph of its ordered pairs. Really, you can graph any function by making a table of ordered pairs and sketching it. So let's just look at example 5, where we have to graph the function g of x is equal to 2x minus 3. So let's set up our x and our y axes. I'm going to go out to positive and negative 7 in each direction. That's what I have room for. So let's make a table of values so we could come up with some ordered pairs. Now, g of x equals 2x minus 3. That's just a linear function. And we went over linear equations in chapter 1. So we see that's in the form y equals mx plus b. Let's just pick some values for x and plug in and solve for y. Because you could think of this as y equals 2x minus 3, right? G of x is the same thing as y. So what if x was 0? Let's pick 0. Plug it into the equation. So 2 times 0 is 0. 0 minus 3 is negative 3. So one ordered pair that's going to be on this line is 0, negative 3. What if x was 2? Plug in 2 into our equation. 2 times x, or 2 times 2 is 4. 4 minus 3 is 1. So another ordered pair that's going to be on this line is 2, 1. Let's pick a negative value. Let's pick negative 1. What if we use negative 1? Plug it into the equation. 2 times negative 1 is negative 2. Minus 3 is going to be negative 5. So there's my third ordered pair. And 3 ordered pairs is enough to graph a line. So let's plot. So we have 0 and then down to negative 3. I have 2, 1, so over 2, up 1. And then I have negative 1 down to negative 5. So that point's going to be right here. And now we could see our line function. And again, it's a little not to scale. Let me do that over. There we go. So it's going to look like that. So that's the function y equals 2x minus 3. So I want you to make the connection that if we have an equation, right, a function in equation form, its graph is just made up of all the ordered pairs that satisfy that particular equation. So let's talk about now how when we look at a graph, how can we tell if the graph represents a function, if the relation that's being, represented in the graph is a function or not? So we have what's called the vertical line test. If any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. And this is why. So let me use this graph as our first example, the one that I just circled, like this oblong circle, oval. Look what happens, and I'll use red because I think it stands out more. If I were to draw a vertical line through this graph, I just picked to draw it there, or I could draw it here, here. Look what happens every time I draw a vertical line through the graph. It hits the graph in more than one spot. And what's significant about these 2 points is that, look, They have the same X value. Both of these red points have the same X value, but they have two different Y values, right? So the same X value is corresponding to Y1, let's call it, and Y2. So this value of X is pointing to Y1, but it's also pointing to Y2, right? It corresponds to two different Y values, and that breaks the rule of being a function. So that's why the vertical line test is nice, because if the vertical line intersects the graph in more than one point, then the graph doesn't define y as a function of x. A function does not exist. So like in this case, for this graph, y is not a function of x because it fails the vertical line test. But look at this graph right here on the left. I have this horizontal line, and no matter where I draw a vertical line, it only hits the graph one time. So y is a function of x in this case because it passes the vertical line test. Let's look at the graph on the bottom left. No matter where I draw a vertical line, it only hits the graph at one spot. So again, it passes the vertical line test, and y is a function of x. And then let's look at this last graph on the bottom right. If I go to draw a vertical line through my graph, look what happens. It hits the graph in more than one spot. Therefore, it doesn't pass the vertical line test, right? And y is not a function of x. So that's how we can look at a graph and determine if y is a function of x. We could perform the vertical line test. Let's look at an example. So we'll look at example 7, where now we have to analyze the graph of a function. So let's suppose we have a function, like in this case, we have variables that are realistic. Like we're going to look at time after infection as a function of the average T cell count for HIV infection. So the horizontal axis is in years. We have 1, 2, 3, all the way up to 11 years, and it's the number of years after a person is infected with HIV. And then on the vertical axis, this is the average number of their T cell count, their blood count. So let's look at the first part of the question in example 7. It says, use the graph to find f of 5, right? The way we say this is f of 5. But what does that mean in the context of this question? So it means, remember, the input is x. So if x is 5 years, what is the output? What's the y value? And y in this case is their T cell count. So what's going to be their average T cell count after 5 years of infection? So let's look for 5, right, for years. And then let's see where it hits the graph, right? This is 5. Go over to the left. What y value does that correspond to? And it's 400. So f of 5 is equal to 400. So at 5 years after infection, the average T cell count is 400. And this is per milliliter of blood. That's the units. Let's look at the second part of the question. So the second part of the question is, for what value of x is f of x equal to 200? So now remember, y is equal to f of x, and I'm telling you that's equal to 200, the output value or the y value. Remember, this represents the blood cell count, the average T cell count. So I'm telling you, okay, when the T cell count is 200, what is the x value? How many years after infection is that? So you see how now we're working the other way around, because I gave you the output and I'm asking for x, which is the input. So we go to 200, right? And let's see where we hit the graph. If we go all the way to the right and we hit it at that point here, which corresponds to an X value of 8 years after infection. So this is a nice example because this graph represents something realistic, right? It's the average T cell count as a function of time after infection. And we were able to answer questions based off of the graph, and we were using function notation, which I introduced above. So this is a nice example. We can also identify domain and range from a function's graph. So in example 8, I gave you 3 different graphs, and I want you to find the domain and range. Now remember, the domain is all of the input, right? So it's the set of all the input. So it's the set of all the X values or the X elements. The range is all the outputs. What are all the possible Y values when we look at the graph? So let's look at example 8. Let's make this a little bit bigger. So let's start with the graph on the left. So we want the domain, which I'll call D, and the range. So whenever we're looking at a graph and we want to find domain, think horizontal, right? Left to right, because we want to know what are all the possible X values. So where is the leftmost part of the graph, right? It doesn't go past -5. Now keep going all the way to the right. Notice how the graph doesn't go past 5. So this graph lives in the horizontal direction between 5 and -5, right? For the X values. And they're included because you have closed circles on -5 and +5. So if I use interval notation, my graph is going to go from -5 to +5, and they're both included, so I'm going to use the square brackets, and that would be interval notation. We could also use set builder notation. So I'm going to write set builder notation also, just in case the homework has you do that. So, or we could use set builder notation. So we could say the domain is all values of X such that X is between -5 and +5. Now let's talk about the range. So now look up and down, vertical direction. What is the range of values, of Y values, that this graph spans? So look at the bottommost portion of the graph. It doesn't go below -4, right? And then the highest the graph goes is +4. It doesn't go above +4. And there's no breaks in between, right? This graph is continuous between -4 and +4. So that's going to be my range. So the range is going to go from -4 to +4. And -4 is included and +4 is included. So I'm going to put close brackets around that interval. If I want to use set builder notation, I'm going to say all values of Y such that Y is between -4 and +4 inclusive. So let's look at the next example. In this graph, we see that there's an arrow indicating this graph continues on to the left, and then there's an arrow indicating the graph goes on to the right. So if we look in the horizontal direction, this graph is going to continue going to the right, and it's also going to continue going to the left, right? And it's going to span horizontally every single possible X value. And there's no breaks in the graph, so the domain is going to be your set of all real numbers. It could be anything from -infinity to +infinity. Or we could say all real numbers. Now let's look at the range. So I see my graph never goes below -2, right? It's equal to -2 over here. And it never goes above +2. So my graph, in terms of the range, can be anywhere from -2 to +2. So my range in interval notation is going to go from -2 to +2. And if I want to write this in set builder notation, we could say all values of y such that y is between -2 and +2. And let's do one more. Let's look at the third graph. Same thing. Let's identify the domain and the range. So let's look horizontally, right? We're going to look horizontally first. So the graph does not really the graph starts at 0, right? It starts at this point right here, but for x, this is 0. We're talking range, I'm sorry, domain first. So let's look horizontally. So this x value right here is 0. And this graph just keeps increasing indefinitely, right? It's continuous and it keeps increasing to the right. So x could be anything from 0 all the way to +infinity, right? Because that graph continues in the horizontal direction towards all your positive values of x. So 0 to infinity. Or in set builder notation, we can say all values of x such that x is greater than or equal to 0, right? Anything 0 and above. Now for the range, if we look in the vertical direction, the lowest y value on this graph is 1. So y could be 1 and anything higher, right? Because you see how this graph is going to keep continuing to increase forever. So it's going to go from 1 to +infinity. And that's going to be my range. Or I could say all values of y such that y is greater than or equal to 1. So 1 to infinity. So those are 3 nice examples of looking at a graph and determining the graph's domain and range. So now we have identifying intercepts from a function's graph. So sometimes we might be interested in if a graph has an x-intercept or a y-intercept. So an x-intercept is where the graph crosses the x-axis. And a y-intercept is where the graph crosses the y-axis. And a function can have more than one x-intercept, but it can have at most one y-intercept, because if it had more than one y-intercept, it wouldn't pass the vertical line test. So let's just practice identifying. So look at example 9. And let's identify the x and y intercepts. Let's do the x-intercepts first. So go across the x-axis, and wherever you see an intercept or an intersection, wherever the graph intersects the x-axis, that's an x-intercept. So the leftmost point is the point -3, 0. This middle point here, if I erase, well, the graph is covering, but it's -1, right? So it's going to be -1, 0. And then the third x-intercept crosses at x equals 2. So that point's going to be 2, 0. So this graph has three x-intercepts. Now, if we look, this graph crosses the y-axis at one point, and that's its y-intercept. And it crosses at the point 0, -6. So it has one y-intercept at 0, -6. So that's the difference between your x and your y-intercepts. And we'll do one more example where we're going to kind of put it all together. So let's use a graph and analyze the function. So we're going to analyze the graph of a function. So here's an example of a function. So I gave you the graph of a function, and let's practice finding domain range. We'll use function notation. So in C, it says find f of 3. For D, at what value of x is the function equal to -1? And then we'll find the y-intercept. So we're going to put it all together, a lot of what we learned in this section. So what's the domain of f of x? So look horizontally. We see, so remember, this is x is equal to 0. The smallest x value is 0. And this graph increases up to this point with the open circle, which corresponds to x equals 5. But it's an open circle. So 5 is not included, right? If we have an open circle. So my domain goes from 0, which is included because this is a closed circle, right? This is the point 0, -1, but the x value is 0. And it could assume any value up to 5, but not including 5 because of this open circle. So my domain is 0 to 5, not including 5. Now let's look at the range. So look in the vertical direction, right? So what's the lowest y value that this graph can assume? And it's -1, right? It doesn't go below -1 in the y direction, and it increases up to y equals 5, but it's not included that 5, right? Because it's an open circle. So up to, but not including 5. So the range is going to go from -1 to 5, but not including 5. Now let's find f of 3. So in other words, what is the y value when x is 3, right? That's x, the 3. So here's x is 3, right? Where does it hit the graph? It hits the graph right here. What's that y value? It's 1. So f of 3 is equal to 1. In part D, I'm asking for what value of x is f of x equal to -1. And remember, f of x is the same thing as y. So when is y equal to -1 for what x value? That's what I'm asking. So now let's go to the vertical axis, right? Here's y is equal to -1, and it happens at this x value, and that x value is 0. And then the last part of this is what's the y-intercept? So where does this graph cross the y-axis? And that's right here where I'm circling in red. And that's the point 0, -1. So that would be my y-intercept. And that wraps up section 2.1. In the next lecture, in the next video, we will cover 2.2.